So welcome. We are now going to look at mass transfer. And before we start looking at mass transfer, make sure all your concepts of momentum transfer are clear because we are going to use some of these concepts while solving some problems for mass transfer. So here is what we are going to do now. This is where we are in the syllabus. We are now going to look at parts number 8 and 9. We are going to look at them together because sometimes we will be using macroscopic balances, sometimes we will be using microscopic balances. That's why we are going to look at them together and not separately as we had done for momentum transfer. Just to help you quickly recap and get in a better preparation mode for this part of the syllabus, I would like you to write equation of motion in vector notation for laminar as well as turbulent flows. What is meant by boundary layer? Describe the three regions in universal velocity profile. Write the equations that relate velocity to distance in these three regions. Why is transfer of momentum higher in turbulent flow than laminar flow? So if you answer these questions, you will be in a better shape to understand the material that is coming now in the mass transfer part. So just to quickly recap what we did in momentum transfer, we said that momentum per unit volume is rho vi, and then we wrote a balance for conservation or a balance for forces arising out of convective transfer of momentum, arising out of viscous transfer of momentum, arising out of molecular motion, molecules traveling from different layers, one layer to another layer, causes a force acting on that layer. That's called as a viscous stress or a viscous transport of momentum. And we also saw, when we looked at turbulence, we also saw that how turbulent motion, how motion of eddies from one layer to another layer also transfers momentum and also causes a force, just like we have for the molecular transport when molecules move from one layer to another layer. Momentum transfer in the macroscopic balance part we have seen in all these first 5 parts. Okay, and in all these 5 parts we were concerned with something like overall force or total power or torque or power imparted to the liquid by way of pump. And to get all these things we had used empirical values. Empirical means somebody has done experiment and given a value. We have just used those values for geometries which are similar or for the same geometries. For example, we have used empirical values of friction factor versus Reynolds number. Somebody did experiments and measured the friction factor as a function of Reynolds number, and we have used it for pipes. And correspondingly, the wall stress is an outcome. The friction factor is an outcome of the wall stress. Same way, drag coefficient for spherical particle, we have used 24 by RE, we have used 0.44. We have used those values because they are experimentally observed by some people. We have just used those values. That's the meaning of the word empirical. Or similarly, lift coefficient or power number of the impeller, head number of the impeller, flow number of the impeller, head develop, flow develop, so many things, so many empirical expressions that we used. Say, for example, the pump problem that I gave you. The manufacturer told the head versus flow. That's an empirical because it is based on experiments that the manufacturer has done. So in the macroscopic balances, we have looked at empirical values and we have used those values for solving the problem. On the other hand, when we went to microscopic balances, we derived equations of continuity, we derived equations of motion. For a case of incompressible fluid, of a Newtonian fluid, we call it as a Navier-Stokes equation. We had this, and it was a partial differential equation, and therefore we needed to either use analytical method to solve, provided it could be simplified into a one-dimensional or a two-dimensional problem, and otherwise we had to resort to numerical. Of course, we have not seen the numerical solution, that's beyond the scope right now. But once you get this analytical solution or a numerical solution, what you get is a velocity as a function of time, velocity if it is a unsteady state flow, or velocity as a function of location, distances x, y, and z. Say for example, within the boundary layer, how the Vx changes not only as a function of y but also as a function of x, and how that allows us to get the integral values, in the sense that how it allows us to get, let's say, friction factor for the total plate, or we had used a microscopic balance. We had used turbulent flow pipe flow equation. We broke that down into three layers: the laminar sublayer, buffer layer, turbulent core, and how it allowed us to get a friction factor versus Reynolds number relationship we call as Colebrook equation. So this microscopic balances after integration allows you to get all these macroscopic quantities. That's what we have looked at in all these 6 parts. So you should be very comfortable with either of these approaches. And recall the equation of continuity. If we could write in the velocity form, we could write like this. This is the convective part, the accumulation, pressure term, gravity term. These are the sources of momentum, viscous transport, turbulent transport, and the strains that are there on the fluid motion of, or on the fluid particle or a fluid element. And recall, we had scaled these equations of motion. Recall what we did in the boundary layer. We had scaled the equations of motion, and that allowed us to get some very dramatic results, like delta by L is proportional. Delta by L is, if delta by L is very small, then delta by L is proportional to square root 1 by square root REL, or how delta changes as proportional to square root length. So in the dimensionless form, the coefficients, this coefficient or this coefficient or this coefficient or this coefficient tells us the relative importance of either the viscous stresses with respect to convective forces, the gravity forces with respect to convective transfer of momentum, or the pressure force with respect to convective transfer of momentum. And these are the dimensionless numbers, the one by Euler number, one by Froude number, and one by Reynolds number, that allow us to make simplifications to these equations. One more point: these quantities, the macroscopic quantities, they characterize rate of momentum transfer, and the dimensionless quantities. So, for example, dimensionless tau w is the friction factor. Dimensionless drag force is the drag coefficient. Dimensionless lift force is the lift coefficient. Dimensionless head developed by the impeller is the head number of the impeller. Dimensionless flow generated by the impeller, or flow going through the impeller, is the flow number of the impeller. Dimensionless power that is imparted to the liquid by the impeller is the dimensionless power number. And how these vary with each other, or how these vary with Reynolds number, that allows us to generalize. So two important points I would like you to remember. One is use of these dimensionless numbers: Reynolds number, Froude number, Euler number. Of course, we have not seen Froude and Euler number in that greater detail, but scaling of various phenomena can be done with the help of dimensionless numbers like Reynolds number. That's point number one. Second, the momentum transfer we characterize in terms of dimensionless parameters. Dimensionless parameters are friction factor, drag coefficient, head number, flow number. These are the dimensionless parameters, and we use these dimensionless parameters, which allows us to look at pipes of different sizes, different fluids, different viscosities, gases, liquids, so on and so forth. Right? The dimensionless parameters allow us to relate phenomena at one situation to any other situation. Therefore, these dimensionless parameters are very important, and we like to talk, or we like to characterize phenomena in terms of these dimensionless numbers. So the dimensionless numbers that we have used for momentum transfer, we are relating them to Reynolds number. So the most important point now is, what are the dimensionless numbers for mass transfer, and how do they vary with Reynolds number? That is going to allow us to generalize the solutions and to apply it to different situations. Okay, again, a little bit recap of the momentum transfer. We have viscous transport is arising out of molecular motion. That's given by tau w is minus mu dvx by dy. It is for Newtonian fluid. So this is called as Newton's law of viscosity. And recall the concept of boundary layer. That's a very powerful concept, because we are going to use this boundary layer concept for momentum, for mass transfer, as well as for uh, heat transfer now. So, and within the turbulent boundary layer, if you think about this as a flat plate, at any location, if you see, the velocity profile is like this, and then there is a viscous sublayer, laminar sublayer, there is a buffer layer, and there is a turbulent core. So contribution of eddy viscosity in the viscous sublayer is zero. Motion or transfer is purely by molecular motion, purely by viscosity. In the turbulent core, contribution because of molecular transport is negligible. You have primarily eddies transporting momentum, and in between there is a mixed layer where both these phenomena are important. So we are now going to extend this concept for heat transfer and momentum transfer. Just to think about now, think about heat transfer, because it is easy to visualize. You are partly accustomed to heat transfer when you in your 11th and 12th standard, and therefore that heat transfer concepts, if we develop for microscopic balances, microscopic heat transfer or microscopic heat balance, we can easily extend it to um, um, mass transfer as well. So that's what we are going to do first, microscopic heat balance. So just like we have momentum per unit volume, rho vi, now we can think about enthalpy per unit volume. Enthalpy per unit volume would be rho CPT. It will have units of joules per meter cube. And remember, enthalpy is a scalar. That's an advantage, because when we wrote equation of motion, we had to write one equation of motion. It was a force balance on each direction, force balance in the x direction, y direction, z direction. We had three such equations of motion because momentum is a vector. Now enthalpy is a scalar, so we are not going to need three equations. We are going to just need one conservation equation for enthalpy. And just like we had convective transfer of momentum, we are now going to talk about convective transfer of enthalpy. That's going to be enthalpy per unit volume, rho CPT, multiplied by the volumetric flow rate, meter cube per second. And this is going to have units of watts, or joules per second. It is a rate of enthalpy transferred per unit time, joules per second or watts. Just like we have convective transfer, we have conductive transport also. That is because of molecular motion. And we had seen, so for example, if you're this picture I showed you earlier, so if there is a fire here, we get convection, we get velocity, we get hot air coming out of the fire, and if that hot air, we are receiving heat from that hot air, we call as convection. Whereas if it is heat is being conducted, let's say in a solid, then it is called as conduction arising out of molecular motion. Heat is transmitted, and then that molecular transfer of enthalpy or conductive transport of enthalpy, we can write as by Fourier law as minus k dt by dx. That will give us the flux multiplied by the area of cross section of this rod, if you like. That will tell us the rate of transfer of enthalpy by way of conductive transport. So now, just like you have conduction occurring in any fluid, both these things will happen. You will have convection also, and you will have conduction also. Only thing that radiation right now we are leaving out. So let's not worry about radiation just now. We are not going to look at that just now. We are only going to concern ourselves with convection, and we are only going to concern ourselves with conduction, the bulk motion, convection, and the molecular motion, conduction. Okay, so if we take this as a control volume, think about these pink arrows. These pink arrows tell us the convection, So if you think about this left face of this block, convection is rho CPT, that is the volumetric, that is the enthalpy per unit volume, multiplied by volumetric flow rate coming into this box through this left face. And the volumetric flow rate coming into this box through this left face is Vx multiplied by area perpendicular to the x direction. That is nothing but delta y, delta z. It is through this left face. Similarly, if you think about the right face, the enthalpy per unit volume is rho CPT. Volumetric flow rate at that location is Vx multiplied by delta y, delta z, and it is to be evaluated at x plus delta x. So it tells you the convection in the x direction entering the box, leaving the box. So what comes in because of convection minus what leaves because of convection. Similarly, if there is a velocity in the y direction, look at this arrow through the bottom face entering, that is rho cpt multiplied by vy, area of the bottom face, area of the face perpendicular to the y direction, y axis, it is delta x delta z, bottom face at y, minus rho cpt vy multiplied by delta x delta z at y plus delta y, plus in the z direction the back face, it is entering through the back face, it is leaving through the front face, rho cpt vz multiplied by delta x delta y, that is the back face, rho cpt vz delta x delta y z plus delta z. You should be very clear and we should be able to write all these things very quickly. Now the conductive flux, I can write this blue arrows, if you see, is the conduction in x direction entering, conduction in x direction leaving, conduction in y direction entering, conduction in y direction leaving, conduction in z direction entering, conduction in z direction leaving. So conductive flux in the x direction entering through the left face is qx multiplied by area perpendicular to that x axis, area perpendicular to that conductive flux, delta y delta z. Think about this arrow, think about this rod, heat is being transferred along the rod, area of cross section we take as the cross section of the rod perpendicular to the heat flow, qx delta y delta z at x minus qx delta y delta z at x plus delta x. Same way in the y direction, qy delta x delta z at y minus qy delta x delta z at y plus delta y, qz delta x delta y at z minus qz delta x delta y at z plus. You should be able to write these terms in a blink of an eye. You should be able to write these terms very quickly. You should be able to visualize these things very quickly now. Get these things so clear that even if somebody wakes you in the middle of the night at 4 o'clock in the morning, you are fast asleep, and somebody asks you conductive flux in the x direction, you should be able to rattle out qx delta y delta z. It should be so ingrained into you, how that visualization as well as writing mathematically, you should be so very clear about it. So in out in out in out in out in out in out plus generation due to reaction, you could have a exothermic reaction happening, you could have an endothermic reaction happening, it could be generation due to reaction, there could be a heat source, there could be an electrical heater inside, nuclear reaction happening inside generating heat, so many, it could be cement, the reaction that is happening when cement hardens, that reaction gives out a lot of heat, so cooling of that cement is very essential for proper curing of the cement. So there is a generation term. Generation term is, let's say, source per unit volume, watt per meter cube if you like, multiplied by delta x delta y delta z. So in out in out in minus out in minus out in minus out plus generated must be equal to accumulation. Accumulation would be del by del T of rho cpt enthalpy per unit volume multiplied by delta x delta y delta z. Be very clear about all these things before you go forward. Now it's just a matter of saying that delta x delta y delta z is 0 and tends to 0, and we could write it as differentials. Just one thing I would like to again remind you, that this qx is the conductive flux, and the conductive flux is, we are writing in terms of the Fourier law. If you are writing in terms of flux, what we are writing is the rate divided by area. So flux is nothing but minus kt thermal conductivity multiplied by the gradient in the x direction. So qx is minus kt thermal conductivity dt by dx, qy is minus kt dt by dy, qz is minus kt dt by dz. Now, so if you substitute this here, divide throughout by delta x delta y delta z, use continuity, use incompressible fluid, so take out rho, you will get this equation, rho cp del t by del t, Vx del t by del x, Vy del t by del y, Vz del t by del z, Kt thermal conductivity, del square t by del x square, del square t by del y square, del square t by del z square, plus the source of heat. Okay, I can write it in vector form, Vj del t by del xj. Okay, rho Cp I can divide here, I will get del t by del t plus Vj del t by del xj, alpha thermal diffusivity, Kt by rho Cp is thermal diffusivity, del square t by del xj square plus S by rho Cp. Either this vector notation, or we could write in the vector notation V dot del t plus alpha del square t plus S by rho Cp. Now again, if I want to write for turbulent transport, I would need to incorporate not just the molecular transfer, not just the molecular transfer, not just the conduction arising out of this alpha, but I also need to account for eddy motion, right? Just like we did for momentum transfer. So this alpha we will get replace it by alpha plus alpha t, or here alpha we will replace as alpha plus alpha t. Alpha due to molecular motion, conduction, thermal diffusivity of the material due to molecular motion, thermal diffusivity due to conduction, and thermal diffusivity due to eddy motion. So eddy diffusivity for heat, if you like, just like we had eddy diffusivity for momentum. Mu by rho was eddy diffusivity for momentum. Mu by rho was kinematic viscosity. Eddy diffusivity for momentum arising out of molecular motion, right? Same way here. These are all very similar equations. Okay, let's go forward. Make sure that you get all this, then only go forward. Pause the video. That's the advantage now. You have a video, you can pause anytime, derive, and then only go forward. Okay, so if I scale these variables, we can scale these variables using delta t for scaling temperature. Again, scaling means we want to make all these variables go in from 0 to 1. Why are we doing that? So that the coefficients will tell us the relative importance. We are going to scale the velocity using v average, and we are going to scale the length using d. So very quickly, if you scale this using these variables, you will get these equations, right? I'm just going to tell you very quickly, just before we do that, typical values of thermal diffusivity alpha. These are molecular diffusivity, right? If it's a good conductor like solids, it's about 10 raised to minus 4 meter square per second. Copper, aluminium, silver, and so on and so forth. If the material is an insulator, say glass or polymer, bricks, it is about 10 raised to minus 8 meter square per second. For water, it is about 10 raised to minus 7 meter square per second. I'm just giving you some values to remember. Air, it is about 10 raised to minus 5 meter square per second. Light organics is about 10 raised to minus 8, is like the insulators. Right? Light organic means benzene, toluene, xylene, of that order. So you can see that the values of thermal diffusivity vary considerably depending on how good or bad the material is for conduction of heat. Okay, now if you scale these variables, delta t by del t, del t by del capital T by del small t, if you scale, you will get del t bar multiplied by del t. Okay. Vj you will scale as V average multiplied by Vj bar. So remember our Vj bar, if you like, Vj bar is Vj divided by V average. So these dimensionless variables, they go from 0 to 1. Now T bar, if you like, T bar is temperature divided by delta T. Why we are using delta T is just because that's what is driving the heat. Okay. Temperature difference between here, let's say here, and here, that is what is driving the heat. Okay. Or temperature difference between here, the adiabatic flame temperature, and here, that is the net transfer of enthalpy. Okay. That's why we are saying some delta T. So right now let's not worry about it, let's not worry about it what this delta T is. Okay, alpha is still here. This T we make it dimensionless, del xj square we make it dimensionless, and I get this term. Okay, now I can divide throughout by delta T, or delta T I can divide here, and I will write delta T on the right hand side here. Okay. That's what we get here. Okay. I can also divide throughout by V average, and I can multiply throughout by D if you like. Okay, that's what we have done, multiplied throughout by D and divided by V average. So that's what we get. Look at this expression. This term now is going to tell us relative importance. So this is made dimensional, it is going to vary from 0 to 1. This is made dimensional, it is going to vary from 0 to 1. This is some dimensionless source term. Right now let's not worry about this term, let's not worry about this term. There's no reaction happening, there's no curing, there's no nuclear reaction, there's no heat being generated by electricity or whatever. So S bar is 0, let's say right now. So this term alpha plus alpha t divided by d V average is going to tell us the relative importance of conductive transport to convective transport. Let's look at this first term alpha by, let's look at this first term alpha by dV average. Reciprocal, I can write dV average by alpha, and we call this as Peclet number, P-E-C-L-E-C, Peclet number. Peclet number. Look at this, we can rewrite this as dV average by nu kinematic viscosity multiplied by kinematic viscosity divided by thermal diffusivity. So the first one you know very well is Reynolds number. Second one is called as Prandtl number. Prandtl number, P-R-A-N-D-T-L. Prandtl number is written as is kinematic diffusivity or kinematic viscosity divided by alpha. What is it? What does it tell you? It tells you the ratio of momentum transfer by molecular motion to enthalpy transfer by molecular motion. We will see what that is in a little while. Okay. Same way you can have a turbulent Peclet number for turbulent transport arising out of the eddy motion. Arising out of this eddy motion. And we can write that as turbulent Reynolds number. This number dV average by turbulent viscosity or turbulent eddy, turbulent diffusivity, and nu t by alpha t. So Prandtl number for turbulent flow, we can call it as turbulent Prandtl number. So this is molecular Prandtl number, the first one, and the second one is turbulent Prandtl number. It is the ratio of diffusivity for momentum arising out of the eddy motion, nu t, divided by diffusivity for thermal diffusivity, alpha, because of turbulence, thermal diffusivity because of eddy motion. Let's not worry about this just now, it's beyond the scope of this syllabus right now. We will only focus on this Prandtl number. Why is it useful, and what do we get from here? Okay, here is the definition, here is the more in depth. Prandtl number is a ratio of kinematic viscosity or momentum diffusivity divided by thermal diffusivity. Now remember, if you think about this boundary layer thickness, imagine there is a plate, it is at a temperature Tw and the fluid is at a temperature T infinity. Okay, let's say T infinity is less than Tw just now. So heat is being transferred from the plate to this fluid. Okay, you can see temperature being plotted on this axis, distance on this axis. Okay, just like we had plotted velocity on this axis versus distance along the y-axis. Right? So we had said that velocity changes from 0 to a free stream value u infinity, u0, u infinity, whatever you like, and then there is something called as a boundary layer, thermal boundary layer, and now momentum boundary layer as well. So momentum boundary layer we have seen already, distance over which the velocity becomes say 99% of v0, right? That's this delta, momentum boundary layer. Okay. Now same way, if temperature variation, if we measure, if we plot, we can calculate a thermal boundary layer thickness as the region where 90% or 95% of the temperature change has occurred. So here for this particular case, this is the thickness of thermal boundary layer. Let's put that in some color. This is the thickness of thermal boundary layer. This is the thermal boundary layer, and this is the momentum boundary layer at this location. Right? How thermal boundary layer, how momentum boundary layer grows with distance, same way thermal boundary layer will also grow with distance. This is how momentum boundary layer grows with distance. This is how thermal boundary layer grows with distance. Now, the thicknesses of these boundary layers are proportional to viscosity. More the viscosity, more the fluid is affected by the presence of wall, so boundary layer thickness will be larger. So thickness of the boundary layer is proportional to thickness of the momentum boundary layer is proportional to kinematic viscosity of the liquid. Same way, thickness of the thermal boundary layer would be proportional to alpha. So when you take this Prandtl number nu by alpha, it is going to tell you the relative importance of the or relative magnitude or the relative size of the momentum boundary layer to the thermal boundary layer. Okay. Look at it the other situation. Prandtl number far less than 1. Here the thermal boundary layer would be now larger than the momentum boundary layer. Now imagine this situation. Typical values of Prandtl number if you calculate. Let's write this Prandtl number. Right? Prandtl number is mu by alpha. If you simplify, nu is mu by rho. And alpha is nothing but mu. I should write properly. Alpha is nothing but thermal conductivity divided by rho Cp. So if you simplify, this Prandtl number would be Cp specific heat mu by thermal conductivity. It's a dimensionless number. Check for yourself. Okay, it's a dimensionless number. Okay, so typical value of Prandtl number for water is 7, air is 1, organics is 20 to 50, hundreds it could be. Liquid metals, it's about 0.01, liquid sodium, liquid mercury, liquid lead. Right? Think about which fluid will give you higher heat transfer rate. So imagine this situation, first situation, Prandtl number greater than 1. Thermal boundary layer is smaller, and thermal boundary layer is smaller means only molecular transfer is happening, because in terms of velocities the convection is very small here. It's very close to the surface, so only viscous transport is happening, and viscous transport being small, only thermal conductivity or thermal conduction will happen here. So that's why very poor heat transfer will happen when Prandtl number is greater than 1. Whereas if you think about this thermal boundary layer and look at the momentum boundary layer, beyond this momentum boundary layer we will have all eddies. So I'm going to have eddies being present in the thermal boundary layer. Eddy, one eddy, two eddy, another eddy, third eddy, fourth eddy. So many eddies are going to be there everywhere here. So in the thermal boundary layer, if eddies are going to be present, and if this delta is very small, if the momentum boundary layer thickness is very small, most of the thermal boundary layer is going to have eddy transport, eddy mixing, eddy transfer of momentum, and therefore heat is going to be transferred very nicely within this thermal boundary layer, and therefore this would be good for heat transfer. So liquid metals like liquid sodium are good for heat transfer, right? Whereas organic materials are very bad for heat transfer. Okay, you will see more of this when you do heat transfer, how different fluids affect the rate of heat transfer. Right now just the concept is important. Lower Prandtl number means you will have better heat transfer. That's the only concept that you should remember just now. So that's why nuclear reactors, when you want a lot of heat transfer, you take liquid metals, say for example liquid sodium as a heat transfer medium for transferring heat out of the nuclear reaction. Okay, if all this is very clear, make sure that your thermal part is very clear. Conservation equation for enthalpy is very clear. Make sure that this picture is very clear. You are able to understand the mechanism of heat transfer. You are able to write the equation. You are able to write the differential equation. You are able to understand the meaning of Reynolds number and Prandtl number. Now you are ready to go to mass transfer. Mass transfer. And in fact, mass transfer we are going to write exactly same way as heat transfer. Only thing is now we'll have to replace in terms of enthalpy balance, enthalpy conservation equation we wrote in terms of enthalpy per unit volume. Now we are going to write a balance for some species that is getting transported. Let's say I spray perfume in a room, those perfume is getting transported. So we are going to write a balance equation conservation equation, mass balance for this perfume now to get transferred across this room. Okay, so momentum per unit volume rho into VI, enthalpy per unit volume rho CPT, mass per unit volume or moles per unit volume, we say concentration of perfume that is getting transferred from within this room, let's say. Okay, so that's what we are going to do. If your momentum transfer is clear, if your heat transfer is clear, mass transfer writing it will be a breeze, will be so straightforward. You won't have to think at all. It uh, just by substituting rho VI by rho CPT. Now that rho CPT will be substituted by concentration of that species for which we are writing material balance. It is so straightforward. Okay, here is what we are going to write now. Okay, we are going to write microscopic species balance. Okay, recall, just like you had heat being transferred by way of conduction and by way of convection. Now again there is going to be a convective transport of this species A. A could be, let's say, perfume. A could be some that I spray in this room. A could be oxygen in this room. A could be nitrogen in this room. I'm going to write a balance for nitrogen or oxygen or perfume in this room. Momentum per unit volume, enthalpy per unit volume. Now mass per unit volume or moles per unit volume we write as concentration, Ca. There is also going to be conduction. We don't call it conduction now. We call it diffusive transport arising out of molecular motion. And just like we had written minus q dt by dx into area, we are going to write diffusivity dm molecular motion into area multiplied by gradient dca by dx. Analogous. There is no equivalent of radiation in mass transfer, so we don't have to worry about this. Only convection and conduction. That's why I'm having this picture again, because heat transfer is so very easy to visualize. I can feel that heat by convection because of wind or because of flow. I can feel the conduction because of molecular transport. Okay. Now material balance for A, if we write over this control volume, again the pink are the convective transfer. Pink arrows are the convective transfer. So if Ca is the concentration multiplied by the volumetric flow rate through this left phase, volumetric flow rate through this left phase is nothing but Vx delta y delta z. It is evaluated at x. Similarly, what goes out is concentration multiplied by Vx into delta y delta z through the right phase. So that gives you the convective transfer in minus out in the x direction. Same way, the pink arrow in the y direction. Pink arrow in the y direction through the bottom face entering, top face leaving. Pink arrow in the z direction. Pink arrow entering in the rear face, back face. Pink arrow leaving the front face. So Ca, we should write this now very quickly. It should be just a flash. Just don't have to think now. Ca multiplied by Vy delta x delta z. Ca Vy delta x delta z at y, y plus delta y. Ca Vz delta x delta y at z. Ca Vz delta x delta y at z plus delta. Very clear. In, out, left, right, in, out, bottom, top, in, out, back, front. Diffusive flux, like just like we had done for conduction of heat. Diffusive flux into delta y delta z. Diffusive flux delta y delta z in the x direction. Look at this blue arrow. Na in the y direction, delta x delta z. This blue arrow. Entering. Na in the y direction, leaving top phase. Na y delta x delta z. Y plus delta y. Z direction. Na z delta x delta z, delta x delta y at z, back phase. Front face, NAZ, delta x delta y at z plus delta z. Generation, so this species A could be generated, it could be a product, it is generated by a reaction happening inside, it could be a reactant, it is destroyed due to reaction in this control volume. S is the rate of destruction or generation. Typically we write R for rate of reaction. Right now, just to help you understand the enthalpy similarity, I'm just writing it as S. Accumulation would be accumulation of A in the control volume. Concentration multiplied by volume, del by del T. Divide throughout by delta X, delta by delta Z, make it go to 0. All these, convert these differences into differential. Do this, pause the video, do it for yourself. Only then you will be able to really understand. Here is the answer now. Na, the flux due to the diffusion, we are going to write as molecular diffusivity dCA by dx, flux in the y direction, molecular diffusivity dCA by dy, flux in the z direction, molecular diffusivity dCA by dz. We call this as Fick's law. Just like we had Fourier law, now it is Fick's law. Okay, molecular diffusivity sometimes is also called as diffusion coefficient. Okay, so you should be able to write this. You should be able to divide throughout by delta X, delta by delta Z. Say, use equation of continuity, and you will get this equation. Get it for yourself. Don't go forward unless you get this equation. You can write it in the vector form, this, or this vector from del form, v dot del CA, v dot del divergence, like divergence, del square CA, okay, plus source. If we have to account for turbulence, just like molecules can transfer mass, now eddies are packets of fluid. So there is a packet of fluid here, let's say at a high concentration of perfume, that eddy goes from here to another location. It is going to transfer that perfume to another location. So eddy transfer of mass, eddy diffusivity, molecular diffusivity is this dm, molecular diffusivity, right? You could write it in this form, Vj del xj or V dot del form. Choose whatever is convenient for you. Okay. Same way, we are going to scale the variables using some value of A, Ca naught. Let's say it could be the maximum value. How much as perfume I have sprayed in this control volume initially. A small place I have sprayed. What is the concentration? Right? V average D, and you can go from here to here. Just a little bit about this molecular diffusivity. This molecular diffusivity not only depends on what is diffusing, it also depends on the medium in which it is diffusing. Say for example, if I have a perfume, think about it. If this perfume is diffusing in air, or if I have a water filled swimming pool and I put the perfume in the swimming pool, naturally the viscosity of the medium will play a part, right? Because the molecules have to travel through that medium. That is the meaning of diffusion. And if the medium has low viscosity, molecules can transfer easily. Molecular motion is rapid. Whereas if it is water, molecules can travel less because of the more proximity of molecules of water in that medium. So diffusivity depends not only on the molecule that is diffusing, solute, it also depends on the medium through which it is diffusing. Let's say that medium is B. So this molecular diffusivity typically write as DAB, meaning the diffusivity of A in the medium B. That's why we write these two values, diffusivity of A and diffusivity of A in what medium. Both have to be specified. What is diffusing and through what medium it is diffusing. Okay. So typical values of diffusivity, let's say oxygen diffusivity in water if you want, right? It's in meter square per second, that's the SI unit. Or in liquids it's about 10 raised to minus 9. In gases it's about 10 raised to minus 5. In solids like membranes, it could be of the order of 10 raised to minus 10, minus 11, minus 12, as low as minus 14, 15 of that order. You see how diffusivity varies with the medium. It is diffusivity of the same substance by the, let's say oxygen. So diffusivity of oxygen in water, right? That's what helps us to breathe. That's what helps fish and all these aquatic animals to breathe. In gases, oxygen diffusivity in gas, air, that's what helps us to breathe. 10 raised to minus 5, much larger. In solid, if you have oxygen diffusing in solid, let's say in a cell or a bunch of cell in an organ, oxygen is being transferred from blood into that matrix, into that tissue which is made up of cells. Oxygen has to diffuse through those that tissue, that can be very, very small, of the order of 10 raised to minus 9 to 10 raised to minus 10 to 10 raised to minus 14. Important point is molecular diffusivity depends on not just the solute, it also depends on the medium through which it is diffused. So if you now, okay, make it dimensionless as before, okay, you should get this expression. Do it for yourself, get it for yourself. Okay. I'm not going to do it now, it should be very straightforward now. Multiplied throughout by D, divided throughout by V average. Look at this term. Let's say there is no source term just now, let's not worry about this. Look at this term. This term tells you the relative importance of viscous, in the sense molecular transfer of A because of molecular diffusion, divided by the convective transfer of A because of convection. Right? So we are not going to call this as Prandtl number, we are going to call it so just small error, let me just correct that error. Okay, I've corrected that error now. So it is Peclet number, dV average by molecular diffusivity, molecular Peclet number, or Peclet number for molecular diffusion, Peclet number for turbulent diffusion. Instead of molecular diffusivity, we have turbulent diffusivity arising out of eddy motion. So this we can write as dV average by nu, kinematic viscosity, that is the Reynolds number, and kinematic viscosity divided by molecular diffusivity, it is called as Schmid number. Okay. Same way we can write it as turbulent Reynolds number and turbulent Schmid number. Let's not worry about turbulent flow just now. Let's go forward. The Schmid number is ratio of kinematic viscosity, means diffusivity for momentum divided by diffusivity for mass, diffusivity of this A. And just like we have now, we talked about momentum boundary layer, thermal boundary layer. Now think about concentration boundary layer. Imagine that there is a plate here. That plate contains high concentration and it is diffusing into this bulk, and the bulk concentration is lower, C infinity. Okay. So we can plot, just like we plotted velocity as a function of distance in the y direction, we can now plot concentration on this axis and as a function of distance along the y-axis. So you see now distance over which the concentration changes from Cw to C infinity, say 95% or 90% of that, we are going to call as concentration boundary layer, right? And therefore Schmidt number is going to be proportional, or is going to be similar to a ratio of these boundary layer thicknesses, delta by delta C. So Schmidt number greater than 1 means delta by delta is greater than delta C. Schmidt number less than 1 is going to mean that concentration boundary layer is larger than the momentum boundary layer, and if momentum boundary layer is small, you will have eddies present within the concentration boundary layer, whereas in this concentration boundary layer there is only molecular transfer. Molecules are transferring because the velocities are small. It is still a very small portion of the, we are looking at a very small distance into the momentum boundary layer, right? So concentration boundary layer, and therefore Schmidt number less than 1 is good for mass transfer. Typical values of Schmidt number for diffusion. Schmidt number you can define like this. Schmidt number is kinematic viscosity, it is mu by rho, and this molecular diffusivity is there, dm, or molecular diffusivity for that A in that medium B. Okay. You can calculate these values for diffusion through water or diffusion through air. Okay. We'll see these values, we'll calculate all these values and use it for problems. Okay. That's the physical meaning of Schmidt number. The things that we have done so far, momentum transfer, conservation equation for momentum or force, equation of motion, Navier-Stokes equation. For enthalpy, for species, we have seen Prandtl number, we have seen Schmidt number. These are all intellectually heavy concepts. You have to think, you have to visualize, you have to understand, only then go forward. Don't just go through these lectures as if it's some as if it's some TV serial, right? These concepts are going to be required again and again and again, and unless these concepts are clear, future courses will be that much more difficult. If these concepts are understood clearly, future concepts will be a breeze. If you write these three equations and you're able to solve these equations, you are a chemical engineer. That's all chemical engineers do, solve these equations with respect to different considerations for different geometries. It's important. Drug delivery, chemical reactors, biological systems, anywhere you think about, these equations are going to be required again and again. So make sure that these concepts are clear, and only way you make these concepts clear is to revise them, to solve problems, and these problems we'll solve in the coming lectures. Let's go forward. Only a small part left now for this lecture. Let's go forward. Okay, just to recap, I have put all the concepts of momentum transfer, heat transfer, mass transfer in one shot. So property per unit volume, momentum per unit volume, enthalpy per unit volume, mass or moles per unit volume. Convective transport, rho Vx, Vx delta y delta z in the x direction. Remember, rho Cpt, Vx delta y delta z in the x direction. Ca, Vx delta y delta z in the x direction. Flux due to molecular motion, viscous stresses, tau ix. Flux due to conduction, Qx. Flux due to molecular motion, Na, in the x direction. Constitutive equation, what equation relates tau ix? Tau ix is minus mu dvx by dy. What do we call that as? Newton's law of viscosity. Constitutive equation for heat transfer, Qx is minus kT, thermal conductivity, temperature gradient, Fourier law. Flux, sodium, flux NaX is minus dm dCA by dx, concentration gradient. Call it as Fick's law. We'll see a little bit more about Fick's law. It's not just straightforward as this, but it's a little bit more involved. This is just a simplified version. Okay. Velocity gradient or momentum per unit volume gradient, enthalpy per unit volume gradient, concentration or mass per unit volume gradient. Newton's law, Fourier's law, Fick's law. Conservation equation. You see how similar it is. Del B by del T, del T by del T, del C by del T. Vj del V by del Vi by del Xj, Vj del T by del Xj, Vj del Ca by del Xj. Pressure term, gravity term, source or sink. Mu del square V by Vi by del Xj square, alpha del square T by del Xj square, diffusivity del square Ca by del Xj square. What are the dimensionless numbers that come out of these equations? Reynolds number, Euler number, Franck number. What comes from here? Reynolds number and Prandtl number. What comes from here? Reynolds number and Schmidt number. Prandtl number is nu by alpha, Schmidt number is nu by diffusivity, Cp mu by thermal conductivity, mu by d rho. Microscopic, in terms of the macroscopic parameters, what momentum transfer macroscopic parameters we have seen? Tau w, f, k, c0, cv, nh, nq, np, cd, cm. They could be either in terms of forces or they could be in terms of dimensionless numbers. K is our resistance coefficient or head loss coefficient for different fittings. Same way, the dimensional parameter for macroscopic heat transfer we will call as heat transfer coefficient. We'll see a lot more detail in the heat transfer course. Mass transfer, the macroscopic parameter we don't call as mass transfer coefficient. Remember our wet bulb temperature derivation, we had said that there is a wet bulb, there is a wet cloth around this wet bulb. Mass transfer happens from here to here, and we wrote rate as proportional to humidity driving force, delta H. Humidity at the wet bulb condition minus the humidity of air. Proportionality constant. We wrote as mass transfer coefficient. That is this mass transfer coefficient. And of course, area is there, that will give you rate. If you divide a rate by area, rate divided by area, if you do, that is nothing but flux, right? So then you will have to rub out this area from here. Let me rub this, right? And let me also write this as humidity at the wet bulb condition minus humidity at the air. And same way we wrote heat transfer. Rate of heat transfer is temperature difference between the air and the wet bulb temperature, and the heat transfer coefficient we wrote it as H. We might have said U, doesn't matter just now. Okay, we are going to see more about this mass transfer coefficient in the next coming 2-3 lectures. Okay. This just shows you that they are all analogous. So whether you are doing momentum transfer, whether you are doing heat transfer, whether you are doing mass transfer, they are all analogous to each other. It is very easy to think of one from the other. In a nutshell, these are called as transport phenomena. Transport phenomena. That's why the Bird Stewart Lightfoot's book is called as transport phenomena. You have all the three transfers being dealt in the same book. Chapter or part 1 deals with momentum transfer, part 2 deals with heat transfer, part 3 deals with mass transfer. Open that book, just read the index. It is so very interesting just to read the index and see how these are dealt with in an analogous chapters in each part of that book. Okay, homework for you. So mass or heat transfer, just like we had done momentum transfer, we are going to do mass or heat transfer. Mass transfer in this course, heat transfer in a later course. We could have a microscopic balance. If the flow is laminar or there is no flow situation, we will use this. If the flow is turbulent, we will use this. So once I use this or this, we have to simplify further, get a numerical or analytical solution. We'll get concentration profile, and then using that concentration profile, if we integrate, we'll get rate of mass transfer. Or in a macroscopic sense, we are going to say that rate is proportional to Ka delta C, or flux is equal to K into delta C. And we are going to use this K to write this macroscopic balance, and then we have to use K from empirical equations. We have to write it in terms of the dimensionless form, dimensionless mass transfer coefficient, just like we had dimensionless force tau W as friction factor. We are going to have to write dimensionless mass transfer coefficient, and we are going to relate the dimensionless mass transfer coefficient in terms of Reynolds number and Schmidt number. Just like we said friction factor is related to Reynolds number, or estimate K using theories and analogies. We are going to focus on these two parts now in the coming lectures. Okay, what we have done so far about Fick's law diffusion coefficient, it is there in a couple of books. Of course, Bird Stewart Lightfoot's book. In terms of a simpler book, if you want to read, there is a book on fundamentals of momentum, heat and mass transfer by Welty, Wicks. 6th edition, if you see, it's chapter 24, sections 24.1, 24.2. And the microscopic balances we did for mass transfer, it is in chapter 25 of that book. So you can refer to that and get yourself more familiar. Okay. This is what I wanted to cover in this part of the lecture. Make sure that these concepts are clear to you, because we are going to start using these concepts for solving problems from next class. These concepts should be so firmly ingrained in your brain. Anytime, middle of the night, even if somebody wakes you and asks you Vx multiplied by what to give you convection, delta y delta z, it should be so clear to you. Okay. These three equations, equation of motion, enthalpy conservation, species conservation, that's all you are going to need forever in your life, no matter what subject you are going to look at. If these three you are doing and you are able to solve, you are 100% chemical engineer even in second year. Let me assure you that. Third year, fourth year, just more practice, trying it out for different situations. Okay. Don't believe me, experience it for yourself. In the third year, go back to this lecture and see whether these concepts are used or not used. more problems in the next lecture.